Welcome to Maths with Bob. Today we're looking at the first principles definition of the derivative. Okay, differentiation, integration, the two sides of calculus. Okay, so the first thing we're going to do is we're going to sort of look at this curve, fx equals x squared plus 1, or y equals x squared plus 1. And we've got a point on the curve, A, and we're going to try and work out how would we work out the slope of that particular curve. Now, I'm just going to grab a line. Okay, now, here's a line. Now, how would I work out the slope? Now, first up, if I actually push this line, okay, so it's got a particular slope up against the curve, you can see it's not the slope at A, okay. The slope at A is actually not quite that steep. So let's actually just grab this line and try, okay, here we go. Let's see how we go now. Okay, we're getting pretty good. Okay, here we go. There we are. That wasn't too bad. So we now have a bit of an estimate of the slope of that particular curve at A is actually the slope of that particular line. Now let's actually look into this a little bit further. Okay, how they originally did it was this line was actually originally, okay, let's push it through here, make it what's called a secant. Okay, so at the moment it's a secant. Okay, it's not a tangent. So let's have a quick look. Let's actually okay, have a quick look down here. Say that value, okay, we've got some values here. And actually this particular point here, you can see here, is a little bit further away from the original value. Okay. Okay. Oops, that one's... let's have a look. Sorry, this is not... this line's not terribly parallel, but okay, well... okay, let's move it up a bit. Okay, it's not too good. Okay, but... here we have a x and y coordinate. Let's actually label some of these spots. Okay, let's call this x, and hopefully, if it's well over here, we called f of x. Okay, and over here, let's call this x plus h, a little bit further along than x, h. Okay, a small distance further along the x-axis. Okay, and obviously the value over on the y-axis is f of x plus h now. If you wanted to put some numbers in, you could say, okay, let's actually put some numbers in. Let's quickly put some numbers in. So suppose that's 1. This would be f of 1 over here. F of 1 would be 2. That would be 2. And if that was, say, 2, this would be f of 2. F of 2 would be 5. So that value over there would be about 5. Okay, so we're just doing it generally, algebraically to start with. Now, how do I get the slope of this particular secant? Okay, it's now not a tangent at the moment. So it's so what we would do is we'd look at let's think. Okay, okay. So we could actually work out this rise and this run. So we could actually say that the slope of that secant going through A and some other point. Let's call this other point over here. Let's call that point, say, B. Okay, at this stage we're just leaving it unlabeled, but it has a x value of x plus h and a y value of f of x plus h. Okay. Now, how do we actually generate a formula for the gradient? Well, it'll be, let's have a look. What would the gradient be? Well, it'll be what? F of x plus h, okay, minus f of x, all over the run, which is just h. Okay, that would be, in fact, the gradient of that line. Okay, now what we have to do is we actually have to shrink this width h, and we need to shrink that down. Just see what that would look like. Okay, let's grab this line. I have to move it up here a little bit to shrink, to move it. Now, if I shrink, I've got to shrink h. You can see what's happening. If I shrink h a little bit, let's have a look, say to here. Okay, we can see the gradient is coming down. Okay, let's actually shrink it a bit more. Okay, here we go, shrink it a bit more. So, roughly about here. Okay, let's actually shrink it down to about there. This is, okay, shrinking it down to about here. So you can see if I shrink h there, it's not a bad estimate of the slope of the tangent at the point. Okay, so we've got to try and formalize this idea of shrinking the value of h. And we do that with an idea of limits. and we go, the limit as h tends to, well, what are we shrinking h to? We'd ideally like to shrink it to 0. So we come up with this idea that, okay, the slope of the tangent at A would actually be the limit as h tends to 0, okay, of that expression. Now, let's actually write this different colour. Okay, so let's actually write this down. So we'd say, okay, the limit as h tends to 0 of f of x plus h minus f of x, okay, that's the rise, over the run. Now the run is just the difference in the x's, or x plus h minus x, which is just h. Okay, so that then becomes, okay, the slope of the tangent. Okay, so let's have a look. Let's just move this line back. So this is, well, okay, so we still have, it's a bit too steep at the moment, so let's shrink it down a bit and push it up again here. So basically, as we shrink h, that x plus h value approaches the x value, and we do this through a limiting process, and that limit there is actually the general limit as h tends to 0. And there's a lot of theory about the left-hand and right-hand limits have got to be equal to each other so that the general limit can exist. And so we normally would apply this to continuous curves. Now we give this particular definition a special notation. We say that this is f dash of x. We call it f prime, that slashy prime thing in front of the, or after the f, in front of the brackets of the x there is f slashy prime x. That's called the derivative of the function x. And you can see here it's actually a limiting process of a gradient. It becomes, in actual fact, it becomes the gradient of the actual tangent at the point A. So what we say is that, in fact, the slope of the curve at the point A is equivalent to the slope of the tangent at the point. Okay, let's have a look at some examples. Well, let's look at our first example of finding the derivative by first principles. This is a simple one, y equals 5x squared plus 2. Okay, so the first thing I think we'd always do is we'd always write down in functional notation fx is equal to 5x squared plus 2. Now, we then would write down what f of x plus h was. Okay, we're now putting an x plus a h wherever we see an x in the function. Now, 5 lots of, okay, x plus h all squared plus 2. Okay, now, we normally work this out, and let's have a quick look. This would be equal to, okay, so it's going to be 5 lots of x squared plus 2xh plus h squared plus a 2 on the end. Okay, so that's going to be equal to, what's that, 5x squared plus 10xh plus 5h squared plus just 2 on the end. Okay. Now what we have to do is we have to put that into the definition, and so we just say, okay, this becomes f prime of x, or the derivative of the function is the lim as h tends to 0. Now we have to put all this in. So this, the fx plus h is that long expression, 5x squared plus 10xh plus 5h squared plus 2. And then we have to subtract off f of x. Now f of x was just 5x squared plus 2. Okay, now it's all over h. Okay, we can see that a few things will cancel. I'll just cancel a few things. We have 5x squared and a minus 5x squared. We'd actually have a minus 2 and a plus 2, so the actual plus 2 and the minus 2 would cancel if I expanded that out with that minus sign there. And so we'd end up with, what? The lim as h tends to 0 of 10xh plus 5h squared all over h. Now, when we actually apply limits, okay, sometimes we may have to do a bit of algebraic gymnastics, but here it's pretty easy. We can actually just factor out a h. So we go to the limit as h goes to 0. We take the h out as a common factor. 10x plus 5h. Okay, then, okay. Now we can see we can cancel the h's. So let's cancel the h's. Put ones if you like. Okay, so now what do we do? Well, we now have this expression, the lim as h tends to 0 of 10x plus 5h. Now, one of the easiest things to do with the limits is just substitute the actual limit value in, which we can do in this case. So we go, put h as 0, so we get 10x plus 5 times 0, which is just 10x. Okay, so we should just get 10x. Okay, so this now is the derivative of our function y equals 5x squared plus 2. Okay, so this is the gradient function for the curve, if you like. Let's have a look at another example. Okay, let's have a look at this example. Now we have a function y equals 1 over x plus 2. So let's actually just go through the process again with this one. And so f of x is equal to 1 on x plus 2, as we can see. What is f of x plus h? Oh, x plus h, yeah. Okay, that's going to be 1 over. Now we put in x plus h wherever we see an x, so it's x plus h plus 2. Yeah, that was a very easy substitution. Okay, now let's apply the formula now. So we say, okay, f dash x is equal to, the limit is h tends to 0. Now we have f of x plus h, which is a 1 over x plus h plus 2 minus 1 over ordinary old x plus 2. Okay, and that's still all over h. Okay, yes. Don't forget the h on the bottom. Okay, now this is an algebraic fraction problem now, so we basically have to work out what is the top. Well, I'll just put a 1 on h at the front now, take that 1 on h out and say, okay, what is, well, we still have the limit as well, so let's actually, let's put the limit in first. The lim as h tends to 0, take the 1 on h out, and then work out the algebraic fraction on the top there. Let's just cross multiply x plus 2 minus x plus h plus 2, and just put it all over the common denominator, which is going to be x plus 2. Now don't expand this out, x plus h plus 2. Okay. Okay, so on the top line again, we do get a bit of cancelling going on. So let's actually have a quick look. The x will go with this x. That plus 2 will go with that plus 2, which is a negative on the front there. And so we end up getting just a negative h. Okay, so on the next line, we can just say, okay, it's equal to the limit as h goes to 0. Now 1 of h, there's just a minus h left here, and an x plus a 2, which we're not going to, x plus h plus 2, which we're not going to expand out. Okay. All right. So we can now see, hopefully, that the h's will cancel again. Okay, so let's see. Let's cancel these. This h will cancel with that one, leaving us with minus 1 on the top. Okay, so we end up getting, in this case, equal to the 1 lim, as h goes to 0. You just get a negative 1 over x plus a 2 times an x plus an h plus a 2. Okay, so we now put in h as 0, or we substitute h as 0 because we're taking the limit of this as h goes to 0, and there's only one h there. So we can quite easily plug this in, and we end up getting, the result is, what, minus 1 all over x plus 2 times x plus 2. I'll just write it as x plus 2 squared. Okay. So we now have that the derivative of y equals 1 on x plus 2 is actually the negative of 1 over x plus 2 all squared. Okay, let's try another example. Okay, well, let's have a look at our third example. In this one, this is a very famous example where you have a square root and you have to do a bit of algebraic gymnastics. But let's actually have a look at how we start this and why we need to do that. Well, first up is we know that fx is equal to the square root of x plus 2. That's easy enough. We know that f of x plus h is just equal to, okay, the square root of x plus h plus 2. Okay, that's so far so good. Okay, so let's now put this into the derivative expression here for first principle. So we go, okay, f dash x is equal to the limit as h goes to 0. Now f of x plus h, okay, is the square root of x plus h plus 2. Now minus the square root of x plus 2 all over h. Now, okay, if we actually put h as 0 in at the moment, we'll get 0 over 0. So we have a bit of a problem here we have to try and sort out. And what we have to do is we have to multiply by the conjugate, and we actually realize the numerator, I suppose you could say. So let's actually do this. So we go, okay, f dash x, okay, is equal to the limit as h goes to 0. Now, okay, the square root of x plus h plus 2 minus the square root of x plus 2, that's 1 over h. Now we multiply it by its conjugate, now, which is the square root of x plus h plus 2. Now it's the opposite sign, so it's a positive square root of x plus 2. Now it's all over itself, okay, so it's x plus h plus 2 plus the square root of x plus 2, okay. Alright, so that's just multiplying it by 1. So what we are doing now is we're actually trying to rearrange this expression into something where we can actually take the limit. So we have a situation where we've got now, if you have a quick look, we've got this one minus this one, okay, times this one, okay, plus this one, okay. So we've got a situation where we've got a plus or a minus b times a plus b. So we end up getting, we use the algebraic result, you know that a plus b times a minus b is a squared minus b squared, okay. Okay, all right, so let's use the correct pen here. So it's the limit as h goes to 0. Now we'd end up getting okay, the square root of x plus h plus 2 all squared minus, okay, this is a squared minus b squared, the square root of x plus 2 all squared. Now, okay, that's the top. What's on the bottom? The bottom is a fairly long expression. It's h times the square root of x plus h plus 2 plus the square root of x plus 2. Okay, so the bottom's a bit messy still. Okay, so when we actually, well, square the tops, we can simplify them, which we should be able to see. We get h goes to 0. We're going to just get x plus h plus 2. The square root of that squared is just the expression, minus this expression, x plus 2. And the bottom again, this still messy expression. But it's going to be, we're not going to do much with it. We're just going to substitute h as 0 like before in a minute. Okay, so let's have a look at the top. What does the top do? There are a few things that cancel in the top. Okay, we've got an x and a minus x, a plus 2 and a minus 2. Okay, and then the h will cancel with, let's have a look. Let's actually cancel the h as well. This h will eventually cancel with that h, just leaving us with a 1 on the top. So let's have a look. So what are we left with? Well, we're left with the limit as h goes to 0 of just 1 over this expression, which is the square root of x plus h plus 2 plus the square root of x plus 2. Now, as h goes to 0, obviously that square root of x plus h plus 2 basically becomes another square root of x plus 2. And we have 2 of them on the bottom. So the net result is that this is actually equal to, okay, 1 over 2 lots of the square root of x plus 2. Okay, so this is now the derivative of the square root of x plus 2. Okay, well, thank you for watching. We're going to go into a few more rules of differentiation in the next series. Thank you. Bye for now. And remember, numbers are your friends. Bye.